Almost there, almost there. It was a hash brown. Yeah. All right, here we go. Okay, hi everybody. Okay, so today's hash table lecture, it's a bit of an experiment. There's a thing I had a different idea about how to do this about 5 months ago. And last night around 10 p.m. I was like, okay, I'm gonna do it. So I changed a lot of stuff. There's a couple little glitches here and there, so sorry, but I think it'll be worth it because I think this version of hashing, I was able to explain hash tables to my wife in about 5 minutes with this approach, which was better. So I'm just gonna try it. We'll see how it goes. Anyway, all right. So today we're talking about hash tables, which is maybe even more famous and more important than a binary search tree, and it's an alternative idea. So I'm going to start by talking about sets and maps, and we've seen a bunch of different ways to build both of these things. We saw the array set in lecture 11. We saw binary search trees 3 lectures ago, then 2-3 trees 2 lectures ago, and then left-leaning red-black trees 1 lecture ago. Okay. If we think about the runtime of the operations for each of these versions of a set, we have array sets are slow, they take linear time. Binary search trees, in the worst case, are linear time. 2-3 trees have nice balance guaranteed, and we got log time in the worst case. And LLRBs are also logging. Okay. Now we have some notes. One of them is that, I mean, the worst case for a binary search tree is in, but if you have totally random data, it's log in, which is kind of nice. 2-3 trees were a beautiful idea, but they're really annoying to implement. And LLRBs are cool because they maintain a bijection with the 2-3 tree. The reason that we even went to the trouble of inventing the 2-3 tree was so that we could invent the left-leaning red-black tree. These are hard to implement, but it's only 3 lines of code, but it's hard to actually like think it through and make sure it works. It could take many hours, but it's a nice, simple piece of code. Questions about our framing? Yes.
Yeah. So if all 2-3 trees can be turned into a left-leaning red-black tree, but not all left-leaning red-black trees can be turned into a 2-3 tree, then wouldn't that be an injection?
Well, but if to be a valid left-leaning red-black tree, you have to be able to be turned into a 2-3 tree. I mean, I can draw you a red-black tree, just like making up a tree and making some red and some black, but they won't actually be valid left-leaning red-black trees. There's no way to actually construct them from nothing, right? So if you start with an empty tree and you start adding things, you won't get any of those invalid trees that can't be mapped back to a 2-3 tree. Make sense? Yeah. So it is a true bijection. All right. Now, there are some downsides of the approach we have so far, which is that the keys need to be comparable. And on the BST map lab, you got to see how that works in Java. The syntax K extends to whatever comparable. So we need to be able to ask the question, is X less than Y? But that's not true of all types. Like, what's something you'd put in a set that can't be compared? Like integers, strings, those are all comparable. But what other things might you have? Sets of objects? Sure. Yeah. What else? I mean, it's kind of vague. Yeah. Images, right? Yeah, sets of images. So I have a bunch of images of cats and dogs. You have no way to say which one's less than another necessarily. So can we avoid the need for objects to be comparable? Yeah. And basically that comes down to the point that not all types implement comparable. You have to implement comparable to be put in a BST map. Another thing is our search tree sets, they have great performance, right? Login is really good. 1 billion items is height 30. But we could do better than login. Is that possible? Turns out yes. So that's what we're going to do today. Hash tables are going to get us there. Okay, here's my alternate idea about how to present a hash table. You guys have not seen this before, but the basic, I mentioned it, I think, at a meeting, but the basic idea is, remember our old friend, the ordered linked list. We turn that into a binary search tree by putting the pointer in the middle and doing some kind of shuffling around. This time, my starting point will be a linked list, and they're not in any particular order, and contains and add are obviously slow. If I want to know, is the number 8 in here? I have to iterate over the whole list to find it. If I want to add something, I have to iterate over the whole list to make sure it's not already there, so I don't end up with 2 copies. So I want to do better than that. And now the key idea is, what if we have, well, there's many things we could do. We could do the things we did before, put them in order and add express lanes. That's a skip list. I could put them in order and then turn it into a binary search tree, but we're not going to do that. We're not going to care about the order at all. That's going to be a really big difference. They're not in any particular order. And instead, what I'm going to do, split it into 2 lists. Okay, I'm going to have 2 lists, one for the odd items and one for the even items. So here, 4, 8, and 2 are over here. 9, 3, 5, and 1 are in the odd list. And I hope you feel comfortable saying that as long as the items are evenly distributed between these 2 lists, adding contains will be twice as fast as if you had 1 list. Any controversy there? So new integer comes in. All I can do with now is integers, but if an integer comes in, I just say if it's odd, put an odd list. If it's even, I put in the even list. How do I know if a number is odd in Java? Mod 2, right? Mod 2 is it equal to 1. Okay, what if we had 10 lists? All right. How do we decide which integers go in which list? So imagine I have 3, 4, 5, 6, 7, 8, 10, 11, 12, 13, 14, 15. Where do those numbers go in my list if I have a set? And how much faster is this approach? I'll give you guys 30 seconds to think about where they might go. Okay, what do you think? Where do they go? Where does 3 go? 3, great. Where does 13 go? 3. Okay, so you could use the trailing digit, for example, which is mod 10. Are there other possibilities? Sure. What's something else you could do? Put them all where? What? Or what's another possibility other than modding by 10? Let's just be creative for a moment. Mod 15, sure. Yeah, you could do mod 15, but then the problem is when you get like 13, where does that go? I don't like that one. All right, another one. You could just get a bitsy thing. I don't know. You could do leading digit. If you did leading digit, what would happen? Like one of these lists would have a lot of items. Which one? 1. Okay. Which one do you like better? Leading digit or trailing digit for this data set? Trailing. Why is it better? They're more evenly distributed. Okay. Right. So that's the basic idea. There's many different possible functions, but I'm going to use mod. Just very natural. It's going to generalize well. Okay. But I won't acknowledge those other possibilities. Okay. So what we have now is what I'll call an array of list set. Okay. Oh, and the other question I had is, how much faster will it be if they're evenly distributed compared to the original approach with just one list? 10 times faster. Right. Item or operations take 1/10 the time. So this is a picture of the universe. So the way our data structure works is if I insert a big old number like this one, I will convert it into an index, and that conversion process I'll call reduction. So it gets reduced into an index, and I picked mod 10. But you could also pick leading digit or number of digits or whatever else. And that gives me back an index, and that index is which list it goes into. So here's a bunch of numbers, the ones that end in 8, guess what? Those mod 8 are 8. And so overall, we get an m-fold speed up if the items are evenly distributed. Of course, if I keep inserting a bunch of items that have 0 at the end, I'm right where I started. But assuming, just for the moment, that the items are evenly distributed, we're in good shape. Okay, any questions about this array of lists set? Okay. Yeah. So it's just an implementation of the set interface. And the way it's done is array of lists. Right. So it's kind of the convention we had, like weighted quick union disjoint sets, maybe, I guess. I don't know if we actually said that in the title, but yeah. Like we had array set, we have, oh, there's tree map and tree set in Java, for example. It's that same idea. Like the last part is the interface, the first part is the technique. Yeah. All right. Now I want to note the word bucket. A lot of times this kind of data structure, a hash table will be a variant of this. Each list is sometimes called a bucket, and you can have any number of items in a bucket, and the distribution of items across your buckets is based on your reduction function. And so, of course, as I mentioned, you could do other reductions that are worse, but I like this one. I think that modulus is the most natural and best reduction function. At the very end of lecture today, we'll see a slightly different version than using the % operator in Java. Okay. All right. So moving on, let's try to make things a little better. All right. So let's suppose we go even crazier and we decide there are as many lists as there are integers. So instead of just having 10, I just have, well, however many integers there are. And that's a weird way of saying that, but I'll say each integer gets its own list, like 1 is in list 1 and 6 is in list 6 and 99,384,983 is in the list numbered 99,384,983. So I hope it's clear here that this would be trivially constant time operations. Contains is you just check if the list is empty, and you add the list. We could optimize this instead of actually storing the number. We could do a Boolean or something, sure, but this idea is very simple on its own. So what are some obvious issues here? Yeah. Yeah, we're just using an enormous amount of space, and it's incredibly enormous amount of space, right? This approach would be wasteful. If you had a language where there's any number allowed, you would actually need infinite memory. Not so great. Now in Java, it turns out, and we'll talk about this again in a little bit, but there is the smallest integer. It's this right here, -2 billion, 147 million, etc. And the largest number is 2.1 billion. And so change. So we need an array of length slightly greater than 4 billion in order to implement such a data structure. Not so ideal. Anybody want to guess why the smallest integer is smaller than the biggest integer is big? 61C material, but someone had their idea, which is 0. 0 has to be somewhere, so they put 0 on the positive side of the space. Okay, yeah. So all of these lists would be another object. It'd be instances of some linked list class. So not only would you need the 4 billion array entries, you'd also need the 4 billion lists if it was full. Yeah, that was 8 billion, I guess. Lots of memory boxes. Big problems. Okay. But it is a conceptual data structure that we could build. So we've seen a trade-off. For m equal to 10, we got a 10x speed up. For m equal to the number of integers, we get constant time operations. So I want to find a happy medium. What m should we pick? I'll let you think about this for a minute. And the answer is a little outside the box. Okay. Good luck. Think of a way.
I guess, but you could do some index so you could I can sometimes
Okay. All right. I'll take some thoughts. What do you think? Anybody want to throw out some ideas here? I gotta go back. Okay. All right. Anybody want to give me an idea? Yeah. Square root of m. M should be square root of number of integers. Oh yeah. Number of integers. I mean, if you had to pick a number, sure, that feels kind of like nice, but there's a better approach. So pick some largish constant. Okay, that could be a better approach than 10 or infinite. Yeah. Mm-hmm. Number of integers. All right. So this is more pick an m equal to. Okay. Pick an m equal to. Okay. Anybody think of anything that's not pick an m equal to? This is like sort of a weird idea. Yeah. Yeah. Do some kind of resizing. I like that. Okay. So in other words, don't pick m in advance. Start at some m, make it bigger when necessary. So it turns out that actually that's a perfectly reasonable approach, and it's actually very natural. And the concept is very straightforward. The idea is going to be very much like an A-list or an array deck, and it works basically like this. Okay, so I'm going to make up a rule, just a totally arbitrary rule, that when we start, n is 0, meaning there's nothing in there. You agree I've inserted no numbers. And m is 4. There's 4 buckets. And then I'm going to keep track of n over m, which I'll call the load factor. In an array deck, when did we resize? When n over m reached what? When do we make it bigger? When it was full, when n over m was 1. Why did we do that? Because then there was no more room. Here, I'm letting 1 be bigger, or letting n over m be bigger than 1. And the idea is there is like, I'm not totally out of space once I get to 1.5. This is a totally arbitrary constant. I could have picked 0.75. I could have picked 4. I could have picked 1.5, and that's the one I picked because it fits in the slide nicely. Okay, so yeah, it works well. So what we're gonna do is anytime we have n items divided by m buckets exceeding or equal to 1.5, we're gonna double the number of buckets. So the first number I'm gonna put in is 7. Where does 7 go? We do 7 modulus 4. Okay, 1, 2, so 0, 1, 2, 3, 4, 5, 6. Wait, sorry. 0, 1, 2, 3, 4, 5, 6. Did I mess it up? 4 0 0 1 2 3 ah. I was up until 1 in the morning, and then I woke up at 6:30. So you guys could do the modules better than I. I always worry about messing up things like logarithms because then I'd feel really dumb. But messing this up, I feel no shame because it's so ridiculous. All right, 4 7. All right, here you go. Watch 0 1 2 3 4 5 6 7. Woo! All right, all right, all right. Next, I add 16. 16 mod 4. It's a multiple of 4, so it must be 0. N is 2. M is 4. Okay, next along comes 3. 3 is mod 4, 3. Next is add 11. 11 mod 4 is also 3 because it's 4, 5, 6, 7, 8, 9, 10, 11. Then we add 20. And this is where, like, in an array deck, we would have had to resize because we're out of room, but here we're creating lists, so that's fine. N over M, our load factor, is up to 1.25. And now when I add 13, I've reached a critical juncture where I decide I'm nervous. I want more buckets. Like, that's too many. Now, this is a totally arbitrary number, 1.5. Literally doesn't matter where I pick, as long as it's some number. And at this point, we'll double the size of our array. Okay. Questions about this before we do the doubling? All right. I don't actually have a Yelke question, but you can either think of it as a Yelke question. When I add 13, I resize. And the process of that resizing is going to involve everything. Now, I'm going to note our reduction function changes. It used to be mod 4. Now it's what? Mod 8. So all of these items need to go somewhere. Okay. So question for you is, where does the 11 go? And if you want, maybe not now, but if you want later, you could draw the results after you double M, all the numbers. But figure out where 11 goes. I'll just give you guys 30 seconds to think about that. This is not an actual Yelke question, just a Yelke-esque question. Another thing you think about is, are there any numbers that used to be buddies that are not buddies anymore? Or vice versa? Okay, I'll show you what happens after you resize, as the numbers end up in these positions. Okay, so 3 and 11, they were buddies with 7, but now 7's all by itself, just by the magic of mod. So things have been spread out a little more. Okay. And items in theory that were not buddies before could now be buddies, but not in a specific example. After the resize, N over M is 0.75. Okay, so that's what I'll call the dynamic array of sets. Dynamic array of lists set. Questions about this? How long did this single operation take, do you think? Like, was this an n time thing or a constant time or what? It's n, right? So you have to build the new array and then you have to copy each item one by one. So make a new array, make 8 new lists, and then copy things over. Okay. So I might call this the dynamic array of list set. Terrible name, but whatever. We're gonna have a better name soon. And it's the same as before, but m will increase as n increases. And if we have n items that are evenly distributed, and again, I'm making this underlined kind of hand wavy thing, like if that were true, then the length of each list will be roughly n over m items. And if n over m is a number which can be, what's the smallest n over m could ever be? 0, there's no items. What's the biggest it could ever be? 1.5. So that's bounded above by a constant. So n over m is constant. The average length of each list is constant. So operations, as long as you're evenly distributed, will be constant on average. Okay. So we'll think about runtime a little more carefully at the very end and what it means about the even distribution, but that's the basic idea. Okay, so this is an idea we could use to store an array of sets in a memory efficient manner that is also very fast. And some way you can think of it as the generalization of the A list, that now it's a set, right? You can store, it's got a very fast add and contains operation. Okay, so it's like we've taken the A list idea, but instead of having like a linear list, we can have an unordered collection where we can have an add and contains operation that are quite fast, constant time, in fact. Okay. In fact, that means it's better than our binary search tree or our 2-3 tree or our left-leaning red-black tree, as long as the items are evenly distributed. Okay. Yeah. Only works for integers, right? But next part we're going to do is generalize. But this is the heart of a hash table. You understand this, you understand 99% of what a hash table is. Okay. All right. So let's go to strings. Strings are a generalization of an integer in a way, and that'll be our launching point for hash tables. So what we're doing right now, by the way, to talk about the context, is we're deriving the idea of a hash table. And after we get to this fifth step, we will have a hash table. What we have is pretty close, but we need one more thing, which is to be able to handle things that are not integers. So let's think about how we could store strings. What we have right now is beautiful for storing integers. And so here's a question for you. Let's say we want to have strings and we have the word cat or the string cat. If we use the same idea, we have a list of items, we have an array of lists. I want to know what is the cat item of a list. One idea that I'll throw out there first, before I give you an open-ended approach, is let's use the order in the alphabet where the first letter is the list number. So for example, cat would go in list number, what, based on this? 3, okay? What are some issues with this idea? What do you think? Like, what's some things that don't seem so good? Yeah. You still, was that, you can't resize. Well, you can resize, but right, almost there. Like there's something like you can resize and you'll get more and more buckets, but well, the buckets, I think there's a, go ahead. Well, okay. You only ever use 26 buckets. Yeah. Right. You can keep adding them, but this approach would never use buckets 27 through infinity, right? Not so good. Okay. That is the main one, actually. There's another issue I have in mind, which is that you can't store other types of strings, right? Like equals. So we end up with all these useless lists, bad buckets. Okay. So what's another idea? And for now, let's just assume we're using lowercase strings in English. So think for a minute about how you would represent the cat item of a list that is better than my idea, which is just use the first letter. Go for it.
Huh? Oh, you. Loki's food is gonna ask today.
All right. Someone throw an idea out there. I'll just put it down. Yeah, go ahead.
Get fries. Get fries.
Yeah, add up all the numbers. Like C equals 3, A equals 1, T equals who knows T? 20. Thank you. Someone whose name is, so are you saying like the result will be 24? Is the answer in your approach 24 in that case? C is 3, A is, yeah, right. Okay. Yeah. That's a better approach than what I had. Other ideas? Sure. Think mod M, right. So for example, cat would be 3. Yeah. Okay. Yep. ASCII and calculate. Well, that doesn't quite get anywhere though, because that's just basically like, see, ASCII if you don't, I'll tell you what ASCII is in a bit. So I'm just gonna table that for now. Yeah. Right. So you're saying like it'd be like 3 times 26 squared plus 1 times 26 plus 20. Right. Yeah, great. All right, that's my approach. Cool. So we're gonna treat, that's exactly what on the slide. We'll treat it as a base 26 number. And I just want to remind you that we already do this in integers with Arabic numerals. So in Arabic numeral, or sorry, in your approach, the version I had on the slide, maybe you had other ideas, sorry, but you hit my idea. The index of cat would be 3 times 26 squared plus 1 times 26 plus 20 times 26 to the 0th, which is 2074. And the reason I'm doing this pattern is that's how decimal works with Arabic numerals. So in Arabic numerals, we have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. If you want numbers bigger than 9, you use a sequence of digits. So 7091 is 7 times 10 to the 3rd plus 0 times 10 squared plus 9 times 10 plus 1 times 10 to the 0th. So our system for strings is the same thing. C, which is 3 times 26 squared. Okay. There's one little difference, which I'm going to note. This isn't super important, but I want to acknowledge it. In decimal numbers, 0, 0, 0 is the same as 0. And strings, A is different from A. Okay. So to fix this, I don't have a 0 in my system. A is 1, not 0. It turns out to work fine. It doesn't really matter. I don't want to talk about it too much. Point being that this is the way we turn cat into a number. Let you try, figure out what B is. So I just want you to write out this expression in your head or on paper or get the actual number. But if I have the word B, powers of 26. That's a typo. Yeah. Yeah. This is just to check and see if what I said made sense. Well, it is the same number, right? I need an integer in Java. I'm just making you understand like what B is. Yeah, yeah. Indeed. All right, B. So it turns out B is 2 times 26 squared plus 5 times 26 plus 5, which is 1487. Okay. So this number is the number we will use to represent the word B. Okay. Now, as long as we pick a base, which is 26 or bigger, someone just asked, the algorithm will give each lowercase English word a unique number. So there's no other word that is 1487. I will not prove this to you, but it is similar to integers. There's no two different integers that are the same number, right? Like 2766. There's no other sequence of Arabic numerals that gives you 2766. It's the same idea here. With that 0, 1 thing, you have to think about carefully. All right. So this is very, very close to a hash table or a hash table. There's an extra step now, which is when I get the word cat, I use an integerization function, which turns it into an integer. In this case, it's 2074. I'll show you what that code looks like in a bit, not now though, because I want to simplify our idea a little bit. And this right here is sometimes, oh, I shouldn't say it's a hash code yet. I'm going to fix, see, I told you there'd be some glitches into an integer representation. It's not a hash code yet. Okay, does not fit the technical definition. It's almost there. The integer is then reduced to a valid index, which we usually use the mod operator. So for example, cat is in bucket 2 because 2 mod 7 is, or 2074 mod 7 is 2. These ones are wrong, but don't check. Okay, anyway, I'll fix them later. Okay. All right, almost a hash table. Okay, we have another issue to talk about, which is integer overflow, which will actually be an ally to us, and it'll make our life a little easier. But we're going to go on kind of a weird side quest here. So using only lowercase English letters is restrictive. We can't write like E, capital G, lowercase g, exclamation point, or Tupac. So we need some way to deal with that fact, like A is 1, C is 26. Someone earlier mentioned ASCII. I'll tell you what that is in a bit if you haven't seen it. The other thing is we need, well, actually, this is the same point. We need some way to decide what exclamation point is. Is that like 39? Is it 106? Is it 2000? Somebody's already done that. And so that'll bring us to ASCII. Who's heard of ASCII? Who's not heard of ASCII? Okay, it's fine. Yeah, cool. Interesting. Why do you know about ASCII? 61A? All right, cool. Ciphers. Okay, cool. So the most basic old school character set currently in use is ASCII format. And the idea is that some people got together in a room one day and decided that the letter capital A is 65 and 97 is the number corresponding to lowercase a and so forth. And that exclamation point is 33 and so forth. So I'm only showing 33 through 126, which are the printable characters. I'll take the question in a sec. I'm showing them below. Turns out, by the way, in Java, you can say character C equals single quotes D, or you can say character C equals 68. And these two pieces of Java code are exactly equivalent. Go ahead.
What are characters 1 through 32?
1 through 32 include things like the beep character, which I think is beep number 7. And if you print it out, it makes a beeping sound on your computer. There's new lines. There's a delete key, which is kind of fun, like a character that represents deletion. There's all kinds of spaces. Yeah, nulls, all kinds of things. Yeah. What's that? Yeah, right. Yeah, there's 2 different new line characters, OD and OA. Yeah. If C was a string, you could not do this. No. Yeah. Yeah. We'll get to Chinese and Japanese in this lecture. Don't worry. Okay. Yeah. Just ASCII here, though, for now. So turns out that because the maximum possible value for English-only text is 126, we can treat our words as base 126 strings instead. So for example, B is not what we said earlier. Now B would be 98. Why 98? Because that's the ASCII table number. E is 101, E is 101. So you get this bigger number if you treat it as base 126. We got Tupac, we have egg, everything's great. Okay, we get big numbers. Okay, so this approach can work. And the code to do this is actually pretty straightforward. So what we do is we start with the integer representation as 0. We iterate over the string and we take what was already there and multiply it by 126. And then we add the next character. And it's kind of a hack. It's a way to implement this function. So how is it that E gets multiplied by 126 3 times? Well, it gets added early, and it's going to be part of the number through 3 cycles of multiplication. So this is a very clever way of writing this code, and I won't say too much about it. Okay. So the question someone brought up was, what if we want to write in languages that are not English? What if we want to cover characters that you can type on your computer that are beyond ASCII? And so it turns out that in Java, characters also support other languages and symbols. So for example, this umbrella character is for the traveler's insurance company or something, as C equals 9,730. This turtle character, which I believe is owl, is equivalent to, I don't know what the tone is 40,140. Here's that turtle. Here's something in Korean. Sorry, I don't know how to pronounce that. What is it? Way. All right, great. That's 54,812. So this encoding is known as Unicode. It is too big to fit on the slide, but it includes basically all character sets you can imagine, and there's always more. So let's suppose we wanted to represent Chinese, okay? In that case, the biggest Chinese character is 40,959. So what we would need to do is use base 40,959. So this is the word goalkeeper. I can't say it. The tones are too hard. I always forget. What is it? There you go. See? Yeah. So that word right there, its integer representation would be 39 trillion, 312 billion, and so forth, which I've helpfully written here with 4 commas, 4 numbers per comma, if that's your style. And basically every character, right? These are 3 character strings in Chinese. This is the one we just showed right here. But if you subtract 1, right, it would be this string. If you add 1, it'd be this string. And this would give every single string in Chinese a unique integer representation, as long as you can keep making bigger and bigger integers. This is the last character in the Unicode character set. I don't know what this thing is. Nobody does. Okay. So you could do that, yeah. Yeah, so this is bigger than the maximum integer. Good observation. Okay, so that will bring us to our last thing, which will get us to hash tables and get us to talk about integer overflow more carefully. Okay. And by the way, this is one of those glitches. Okay. So quick thing. This Chinese character sequence of 3 characters is this number. That's all. It's a base 40,959 number. All right. So what we ended up with mapping goalkeeper as a base 40,959 number is this huge number, but that number doesn't exist in Java. Now, there are other languages that allow this. Like in Python, integers can get however big you want. Maybe your program won't actually run if you pick too big of an integer, but technically the language is defined mathematically as including all integers, but Java no. So as I noted in Java, the range of numbers is between -2 billion and 2 billion. And if you keep adding numbers, when you get to 2,147,483,647 and you add 1, you roll back around to the beginning. So it's like a hidden mod 4 billion-y kind of thing happening. So you just go in circles over and over. So when you overflow, when you try to generate a number that's too big, you just start back at the beginning and you end up at -2.1 billion. There was a video game I played a long time ago when I was a kid called Star Control 2, in which there was a race of very enlightened beings that had become so enlightened and good that they actually rolled all the way back around to evil, having too big of a value. And that was a major plot point of the game. Anyway, so I was very well aware of this as a kid. Also, the biggest number used to be smaller. Like on a traditional program when it was running, you don't run into overflow error super often these days, but yeah, integers, this is what you got. Okay, so because Java has a biggest integer, we don't get the numbers we expect. So for example, omens in base 126, you would expect to be 28 billion, but that's bigger than the maximum integer. So if I use my function that uses base 126 that I showed earlier, it would actually give you -1.867 billion. Okay, is this a big problem? I mean, not really, it turns out, but just acknowledging this, because this will allow me to eventually make this thing into a hash table. The thing we're getting now, because of the fact that Java doesn't let you make arbitrarily big numbers, the set that you're projecting all data onto is how big? 4 billion. It's a finite size. So all of this class, I've been assuming we can make arbitrarily big integers, but actually, because of the restrictions of Java, it's only 4 billion items. And so if we go to Wolfram Alpha, there's a thing called a hash code. What is it? Well, it is a function that takes a value from a set that could be infinitely large, for example, all strings, and then it maps it onto a set with a fixed number of members. Okay, in our case, that fixed number is 4.294 billion, so it's a hash code. Okay, so the integerization function we wrote earlier, because of this overflow issue, it is actually a hash code because the set we're projecting onto is fixed. Okay, so in other words, because the range of our hash code is finite, then I'm going to note something, which is what we have as a hash code. And secondly, I'll note that our goal that I just like made up and never justified of getting a unique representation is impossible. So for example, I have here goalkeeper, which is 23,729,400. And you could try this out. If you do system.out.println, you'll get this number. Oh, I didn't tell you something. Jeez. All right, sorry. Let's go back slide. All right. Hi, guys. Rolling back. As I said, this is new. I'm sloppy. I grinded this one out pretty quick. Okay, so it's impossible to get unique factorizations. That is, this number 39 trillion, you just can't get it in Java. So what Java did is they said, we don't actually care about picking some huge base to ensure uniqueness. Instead, what they did is they said, let's use 31. Okay. All right. So then this first character, you multiply by 31 squared. The second one, you multiply by 31. The last one, you just add it. And you get 23,729,400. Much better. And so I can take this integer and this string and just print out hash code. I'll talk about that in a second. And you'll get this number. Okay. Why 31? It's a small prime. That's one less than 32. But I can't really talk about it in great detail. The basic idea, though, is you don't want your number of buckets to be lined up with this number here. Like imagine that you had 31 buckets. Things could go awry. I won't really talk about that much. I don't really want to go into the math. Maybe I'll sneak it in at some point, but not today. Okay, so they picked 31. Now, because Java picked 31, there's infinitely other strings that map to this same number, 23,729,400. I wrote a program to find such a collision this morning. Actually, ChatGPT wrote a program for me this morning to find this. Turns out that this string of characters from multiple alphabets, including some Mongolian and an unprintable character, gives you 682 billion. And when you do the roll around thing, you keep wrapping around the overflow, you end up at 23,729,400. Okay. So this right here are two numbers that have the same hash code. Okay, so now we finally actually got to the hash table. In fact, we were basically there before, but now we know a little more about integer overflow. And so the idea is that when I get some information like bow bow, right, the string, I compute the hash code and I get some big old number. Okay, maybe those overlap other numbers. We don't care at all. And then we're going to mod by 10 and get an index, and we get like hug, bow bow, pong or something. I don't know how to say it really. Yeah, let's see. I looked this one up. This means nature. And it's, anybody know Arabic? No? Oh yeah. What is it? Oh yeah, there we go. Yeah. What's weird is when you Google translate it, it doesn't put the transliteration of the last ta in there. I don't know why. That really blew my mind. Okay, we got Hindi. This one's fabulous. I remember. Anyway, I don't remember. What's this one? There you go. Great. All right. So all those strings, oh, and Estan, of course. So all these strings here, they have hash codes in Java. They end up in some buckets. Okay. So basic idea, take a string, I turn it into a number, I reduce it using a mod function, I get to where I need to go. And there's a little tiny caveat here. Okay. Any questions about this? So this is the hash table. That's it. It's the whole thing. Yeah. How do you pick your initial size? Doesn't matter. Pick, well, it does matter a little bit. You don't want to just double. There's a doubling schedule. Like, for example, starting at 2 and doubling every time would be a bad strategy. Be a fun question to think about in discussion. Like, you wouldn't want 2, 4, 8, 16, 32, 64. You need the numbers to not line up nicely. That's just sort of the crude answer. Yeah.
Okay, so sorry, and two things, data points and states, do they possibly have the same hash code?
If two what's are distinct?
Data.
Theta values. Why are we talking about thetas? Or where's the letter theta I'm not seeing?
So data.
Data. Oh, data values. Oh, they're distinct. Oh, sorry. Yeah, if two things are distinct, they could certainly have the exact same hash. In fact, here's an example. Yeah. Yep. But it doesn't matter. You have that. You have collisions anyway, right? No matter what. Okay.
So, can I do a little recap?
Recap. Yeah. Bring it on.
Unicode characters, you can represent them. They're kind of unique on its own.
Right.
You feed into a hash function, and then you get the hash code.
Right.
Which some strings will have the same hash.
Right.
code.
The hash codes are not unique.
And then you reduce it to now.
You reduce it to an index, which is just modding by the bucket count. That's the whole thing. That's a hash code. I gotta know. Yeah.
What guarantee does this provide that like still not every value happens to fall into the same?
Right. There's no guarantee whatsoever that things don't fall in the same bucket. And in fact, you can create adversarial inputs to, for example, the Python hash table and elsewise. There is a trick, which is if your items are comparable, what Java does is if it detects the items are comparable, it actually builds a red black binary search tree bucket so that you don't run into trouble. But that's all hidden under the hood. All right. So let's talk a tiny bit about hash tables in Java. And then I might have time to talk about performance and summary, maybe not. So I'll mention that hash tables are the most popular implementation for sets and maps. Like this is what a Python dictionary is. It's this exact idea. The implementations are actually relatively simple to create. Like writing the code for a hash table, you'll see in next week's lab is easier than what you did in last week's lab, which was even easier than the left-leaning variety. So hash tables are relatively easy to implement compared to balanced trees. They don't require items to be comparable, and they're very fast. In Java, they're called hash map and hash set. And one interesting question is we have to know, our data structures have to know how to compute each object's hash code. Now, unlike comparable, it's not like implements hashable. Instead, hash codes are so important, as it is with Python, that every single class, it implements a hash code, or it has a hash code, no matter what. In fact, it's one of the operations. Wrong bolded one, but hey, that's fine. So hash code, that's where the actual implementation resides whenever you have a function. There's a default implementation, which is just return this, turned into a string. Actually, it's return the name of the class plus an @ sign plus this. And that gives you the memory address. So that's the string. Sorry, reset again. All it does is return this, the default hash code, and that's it. So if I look at the actual hash code for the string class in Java, it looks almost exactly like this. I've cleaned up the code very slightly for reasons that you can read about if you want. But basically, it is, and I should say override even, but I didn't. But you would start by saying, let's start at 0, then we'll multiply by 31 and add the next character and repeat that process and over. And if I do that, I get 23,729,400. Good. Now there's lots of different, any string you put out there, it has a hash code. So for example, A and B and this and Kamala Lifefully and some Vietnamese. And I bring up these couple examples here to show that A is really just the ASCII value for A. These two strings collide, and that's totally okay. Who cares? They're just going to end up in the same linked list, guaranteed. And this string in Vietnamese, it's negative. Okay. Well, let's talk about negative real quick. And this will be a little caveat. This is actually called student, sorry. Let's suppose that I have some object whose hash code is -1. Out of curiosity, where do you think this item should go? I'm curious to know which one you like. I think this should work. Let me know if Yelky's link working. What's that? Yeah. All right. I can't actually see the distribution, but I think 3 I like a little better. Some of you might have said it should be 1, and you're not wrong. 1 and 3 are both fine, but here's my argument for why it's 3. Okay. So let's imagine the hash code is 3, then it should go in 3. 2, it goes in 2, 1, it goes in 1, 0, it goes in 0, and then -1, we wrap back around. I like it a little more. That's just me. Okay. But it would be also okay to do 1. Now, if you were to try and do -1 mod 4, turns out the modulus operator in Java is not really a mathematical modulus. It's something a little different. It takes the absolute value, then it mods it, and then it negatives it back, basically, is one way to think about it. So what you'll end up with is index errors. If you use -1 mod 4, you get -1, not so good. If you want the thing that I told you is better, then you could use math.floor mod. So math.floor mod is like a normal mod. Why is it called floor mod? I'm not going to talk about it now, but it does the right thing. You could also do absolute value. You could do what the Princeton textbook does, which is a sort of weird thing. But point being, floor mod gets you 3 when the value is -1, and it generalizes naturally. Okay. So then wrapping up hash tables. How hash tables work is we convert using a hash code method to get an integer representation, which may be negative. And then we use a reduction function, which is, well, in Java, floor mod is the one I recommend. And it's going to be floor mod by 4 in this case, which gives you 0. Question? No? Yeah.
How do we make search fast within the lists that live in each of the?
So how do you make search fast? You don't need to. So I'm going to talk just very briefly about that in the wrap up. Yeah. The runtime of floor mod is, well, it's constant because it's just takes an integer and gets you another integer. Yeah.
Is this still like a dynamic?
This is still dynamic though, this approach. Yeah, every time you resize, you got to take n time, but that's okay. I'm going to skip these warnings. Okay. All right. So I want to talk about what you just said is how do we make things fast? Okay, so it turns out everything will be fast. If we have a fixed number of buckets m, the average list will be around n over m items. But the problem is that as you get more and more items, like n gets bigger and bigger, then if m is 5, and we define q as the load factor, eventually n is going to get really big, and yes, you're 5 times as fast, but you get linear time operations. The thing we did earlier is we had an increasing number of buckets m, which meant that the length of each list is going to be constant as long as items are evenly distributed. Okay, so in other words, the runtime is going to be n over m. So to you, like the way you think about it conceptually is if you have 1,000,000 items, you have, maybe like around 1,000,000 buckets, and that around 1,000,000 buckets, each one's going to be very short, like 1, 2, 3, maybe 5 items. So it'll be pretty fast. So the overall runtime, if you're willing to spend the space, it's going to be about constant. Okay. Now, if there's a resize, it does take more time, and I'll just wrap it up there. Okay. There is, of course, the caveat about even distribution. but it is 2 o'clock, so I'm not going to say anything about it. So this is the summary of the whole thing. I'll talk a little bit more in the next lecture about this. So as I said, this is like a totally off the dome almost lecture. Hope it was fun. Hope hash tables make total sense. All right. Oh, double clap. Twice as long. All right.